time series dengue fever prediction that we worked on term project. Bilge, this is your section.
Okay, so first we started investigating two different cities. When we look at first, we have seen that they have different geography. First of all, when we look at Iquitos, it is in the middle of rainforest and there are many rivers, etc. So the natural conditions are dominating the effect of dengue fever because it is mostly caused by mosquitoes, which depends on some, let's say, certain life conditions, which requires a temperature range, etc. When we look at this Iquitos, we can, since we have in the data set that many natural components, many natural data types, for example, temperature range, dew point, etc. So that's why the data set helps us to predict better in Iquitos. But when we look at San Juan, the temperature range and also the precipitation changes a lot. So that's why actually there are many noise and also many problems in San Juan dataset, because in San Juan it's mostly caused by human activities and the cities around them. And when we look at that, they, as you can see, they have different time range with the total cases, and the temperature range doesn't show that the relation between total cases and the temperature. And when we look at the second page, we will see the temperature, for example, in here doesn't affect the total cases, but when we also look at the diurnal temporal range, which is also important because the mosquitoes can die in sudden changes. So when we look at Iquitos and San Juan, it actually affects the total cases, diurnal temperature range. And then we see that in the multiple years, we can see that there is a trend. For example, when we look at Iquitos, there is actually a trend. We can see that dew point affects the total cases. Why? Because when it increases, for example, in 2004, at the end of the graph, you can see that it increases, and then you can see also increase in 2005 with the total cases. So there is this effect, but it's lagged. So it's postponed. You can see the effect of 50, for example, first week's dew point in the total cases of 2005 first a few weeks. So that's why we added some lags to the features. Let's see the second presentation. So in here we see that some of the datas are not directly affected, but when we combine them in certain conditions, they are actually correlated with the total cases. For example, NDV with the dew point in San Juan, when we look at that, it's not correlated as Iquitos, but it also definitely affects the total cases when they combined. So that's why we added some nonlinear features in which that we combined some interactions that we represent interactions in features. Let's see the other picture as well. So when we look at here with temperature and certain humidity rate levels, when they combine together, again, they will affect the dengue total cases. And also, there is one more explanation that I wanted to do in the next picture. That you can see here in San Juan, the precipitation is again differs a lot. So that's why we add clip. So that we can get rid of the some over parts. For example, we cut some peaks, some noise. Next picture, please.
This is
Mm-hmm.
okay.
In some, we can say that two cities, they have different features. Some features interacts with each other and provides us certain conditions, and also they are correlated with total cases in a different way. So it was obvious from the beginning that we should have use two different models to predict two different cities. It's yours. Stage is yours, Zeynep.
And I will explain the data processing pipeline here. We did some pre-processing features in LSTM. So first, chronological splitting. To avoid optimistic bias from random shuffling, the dataset was split chronologically. The final 52 weeks of training data were reserved for validation. And causal data imputation that we did. Missing values were handled. Signal smoothing and filtering. We did one of the LSTM data preprocessing pipelines. And outlier management, z-score normalization. And we compare four paradigms actually here. First, negative binomial, second, tree ensembles, third, LSTM, and finally, quantum kernel. In this part, I will explain LSTM. LSTM feature engineering. We used some feature engineerings to handle the score. The LSTM model leverages sequence-aware features to capture both short-term triggers and long-term epidemiological memory. So first, we multi-scale lagged features. We added weekly lags, and second, cycle seasonal encoding here. As you see, we add week of year to the transformed into sine and cosine components. And here we roll the statistics, 8 and 26 windows, and refined target handling, use log 1 plus y. And why LSTM? Because Dengue is a time series with delayed feedback, and LSTM learns long-term dependencies, seasonal structure, and nonlinear temporal interactions. So why did the LSTM score improve? I will explain some improvements that we did for improving the score. First, we proper treatments of the target distribution. We add some Dengue case counts are here. Directly learning raw counts forces the model to overfit extreme outbreak peaks. And we stabilize the learning problem using a log transform targets. So we again, I mentioned log 1p y train and y validation here. And second, temporal noise reduction via causal smoothing. Weekly Dengue reports contain reporting noise and short-lived spikes. The LSTM should learn biological trends, not reporting artifacts here. And this prevents memorization of noise and improves generalization. And third, we did sequence learning instead of log memorization. And this helps us to capture delay environmental effects and outperforms static models. And fourth, city-specific model optimization. And here, San Juan and Iquitos exhibit fundamentally different dynamics. So we used this city-specific configuration. And finally, we controlled regularization and early stopping. Overfitting is a major risk due to the limited data here. So we used early stopping and regularization. And finally, the LSTM score improved because we stabilized the target distribution and reduced temporal noise, leveraged sequence-based learning instead of static lags, and optimized the model separately for each city. These changes allowed the LSTM to learn biologically meaningful temporal patterns rather than memorizing short-term fluctuations. And you can see for both city the validation scores. We finally take 3.5 for Saint John and 2.5 for Iquitos. And you can see the Saint John actual versus predicted correction scales. LSTM captures the overall season trend and long-term dynamics. And here the sharp outbreaks, peaks are intentionally smoothed and results in significantly lower MAA compared to tree-based models. And for Iquitos, stable and well aligned with true values, as you see, and reflects more regular here and climate-driven dynamics of Iquitos, actually. And here the feature correlation heat map. This heat map shows strong correlation across lagged and rolling climate features, which makes linear and tree-based models unstable. But LSTM can naturally learn these temporal dependencies without explicit feature selection. And we use negative binomial for polynomial regression part actually, and because we use negative binomial because it's suitable for count data with over dispersion. And purpose here is transparent baseline and interpretable. And limitation here is its linear mean structure, and it struggles with complex and seasonal spikes. And we observed that it works better in Iquitos than Saint John, as in LSTM. And we tried other tree models like Light GBM, XGBoot, and Random Forest. And the scores were not like as we expected. So these are the scores for Saint John and Iquitos separately. And this is actually our first LSTM score. For final, we take Saint John for 3.5 and Iquitos 2.5. But again, it's still the most accurate and high score here for an LSTM. And as you see, negative binomial and random forest and BDT, XGBoost, and Light GBM are actually pretty high. But still in Iquitos, because of the data, it's still more accurate here. And why tree ensembles? Because it captures nonlinear linear relationships between climate variables, and this handles threshold effects like temperature, humidity, and it's naturally support mixed feature types. And how they were used, it's explicit log features and rolling statistics provided as input. And again, it's city specific and no sequential memory. And here the limitation is model long-term temporal dependencies beyond fixed lags. And this is your part, Bilge.
Now, when we look at the quantum machine learning kernel, in quantum, why did we choose it? Because we believe that if we could represent these nonlinear features in Hilbert space, maybe it could provide us a solution, since we have discussed this in our lessons, that sometimes kernel functions can help us, or sometimes when we map the actually the features into a higher dimensional space, it could be better represented. So then the classifier, even though it is let's say it is a linear classifier, it can work better. So we wanted to decide, it was more of a like experimental choice. So that's why we tried this, and we have used different tests in order to optimize hyperparameters. We gathered this solution in the prediction, and then of course this model was built after a few tests. And first I wanted to explain.
Başladı.
We have conducted several tests in order to optimize the hyperparameters, and also we wanted to decide what kind of an architecture should be built. So first we started with performance comparison with increased sample size, and 100 samples and 50 samples are compared in terms of mean absolute error. And you can see that in 100 samples, it actually got worse. And then we conducted another test in order to visualize how would perform a quantum kernel in comparison with RBF polynomial and linear kernels. So as you can see that in San Juan, and also it is actually performed it performed worse. And when we look at also another one, you can see that quantum actually performed better, but we had to overcome under prediction issues in here. Actually, it seems better, but it's not as better as we hope. So you can see the comparison also in here. The quantum kernel is either underperforms. It is not actually in a way of problem solving one. So we also tested the regularization hyperparameter. So it is alpha. And in order to decide what would be the best alpha for our models, we have designed different tests. And then in this test, you can see the results in the table. For example, these configurations are used, and also you can see that 0.1 is the best alpha values in terms of mean and also error. And then you can see that alpha 0.01 is the better choice for alpha for Equitos. But then you can see in Equitos, alpha is not actually, alpha doesn't affect much the error. So as long as it is kept in this actually range, it doesn't matter much which alpha that you used. So that's why we decided to use the same alpha for both cities, which is 0.1. And then we have also this, in the fourth test, we have compared the actually predictions, which ones are the best predictions of the of our model, and which ones would be the worst ones. As you can see, in some cases, it actually performed good, but then it wasn't enough to use as a main model. So also this was an experimental choice. We didn't want it to use as one of the main models, but we wanted to see that how it would contribute. So what did we use in technical part? We used entanglement and data re-uploading enable to model that learn strong representations in low sample settings, because we had restrictions of computation, and because it takes a lot of time in each kernel, in each qubit. When we add more dimension, it is almost impossible to use all data. So it was never meant to as a first choice. And also you can see that at least as I said before, in Equitos, it seemed like it was a better choice because there were less errors. But then we can see that it is also underpredicted. And also in San Juan, it's much better, but then it needs an improvement. So therefore, after all these trials, we didn't decide to use quantum kernel in our actually competition. But I wanted to show you that we conducted all tests in here quantum machine learning tests, IPI, NB. You can check them from here. And then we decided our model, and
which is LSTM.
yes, and then LSTM was used only for submission in here, and it improved in time. You can see all the process of LSTM and also improvements in our files. Thank you for listening.
Thank you for listening.